I hope more audience will join us later. Let's get started in the interest of time. So good morning, everyone. So welcome to the IFAS AI and Data Science Seminar Series. My name is Charlie Lee. I'm a professor in the Agriculture Biological Engineering Department at the UF. I'm also serving as the AI Administrative Coordinator at IFAS. So the seminar series is part of the effort to build a robust scholarly community on AI and data science at IFAS. It provides a platform for both internal and external speakers to share their latest research developments in fundamental and applied AI and data science technologies for agriculture, natural resources, and human systems. We invite volunteers to join our planning committee to shape our seminar series and welcome your suggestions for future potential speakers. So today it is my pleasure to introduce two of our internal speakers, Dr. Daeun Choi and Dr. Chang Zhao. Both are among the UF Provost AI hires. So Dr. Daeun Choi is an assistant professor at the Agriculture Biological Engineering Department based at the Gulf Coast Research Education Center. Daeun joined UF in 2022. Before this, from 2017 to 2021, about 4 years, Daeun served as an assistant professor at Penn State University, where she developed an automated system for mushroom harvesting, robotic fruit tree pruning and thinning, and apple yield forecasting using computer vision techniques. Her research interests lie in precision agriculture combined with drones, robotics, data science, and ICT technology for specialty crops in Florida. Today, she will be presenting on a new approach to training agricultural robotics through synthetic data and digital twin. After a short interval for questions, we will hear from Dr. Chang Zhao, our second speaker. She's also assistant professor in the Department of Agronomy. I will introduce her later. So each presentation will last for about 20 to 25 minutes. We will have a short Q&A session right after each presentation. We look forward to an enlightening discussion, and I encourage you to participate actively in the Q&A session. So Daeun, would you like to share your screen? Go ahead and present your talk. Thanks.
Can you see my screen?
Yes.
Okay, cool. Okay, thank you, Charlie, for introducing me. Again, my name is Daeun. I'm an assistant professor in the Ag and Bioengineering Department. I'm located in GCRC at BOM. Today, I'm thrilled to share with you my lab's latest research on utilizing synthetic data to enhance agricultural AI and robotics technologies for strawberry production. Before we begin, the name of my lab is Smart Agriculture Lab. Our study involves the development and implementation of machine learning and robotics for precision agriculture. By utilizing the latest advancement in AI, we hope to revolutionize the way farmers approach their crop production and ultimately improve the efficiency and profitability of their operations. As you already know, agriculture has faced many challenges in the past decades. Arable land per person is decreasing, and rural areas are experiencing labor scarcity. There are also the energy and climate change problems as well. So we need a new way to increase the productivity. This is nothing new, but across the country, problems have become worse during the pandemic with the inflation of the cost. Especially the labor shortage increased, and many farmers had to waste hundreds of crops due to the unreliability in labor supply. More farmers naturally started to turning towards automated solution and robotics technology. So how can we help to create more reliable and also cost-effective infrastructure utilizing data-powered and automation and robotics? The precision ag is one of those solutions. Precision ag is currently considered as a future farming method that involves using data and technology to optimize farming practices. It is also called as site-specific crop management because the precision agriculture analyze the environment and execute the farming task only where it is necessary. To achieve an enhanced precision culture, we rely on several key technologies, such as AI and machine learning, sensing and robotics that empower us to make data-driven decisions and optimize farming practices. And although AI and robotics can help a lot in farming operation and automation using those technologies, especially developing those technology isn't necessarily easy. One big problem is that they can be very expensive and time consuming, and we need experts to develop and set them up and also maintain. In our lab, we follow a specific process to develop this robotics and AI system for agricultural field. Initially, we designed the system, and then we build the necessary hardware component. And afterward, we collected the data to train AI algorithm and process the data. If we are not happy with the result, we return to the system design process again. Actually, I'm hearing some noise. Can you mute yourself? I'm not sure. Okay, thank you. We return to the system design process, and then we start this entire process again, which can be really time consuming and expensive to repeat this whole process. So how can we reduce this turnaround time, risk, and also cost involved with this developing autonomous system? So one way to solve this problem is by using digital twin technologies. Digital twin is a virtual copies of real farms and can give us useful information before we even start testing the system in the field. Digital twins can also show us different what-if scenarios for AI and robotic system that we cannot really have in the field. By testing and tweaking this scenario in a virtual space first, we can make them understand the environment and surroundings better before we're testing this robotic system on real farms. This cuts down risk and makes this AI and robotic system more robust in real field environment. So we decided to try out digital twin and synthetic data to replace this previous two process system development and data collection to simulation and synthetic data collection. For these processes, we use NVIDIA Omniverse, more specifically IFAS software. The Omniverse is a collaborated platform developed by NVIDIA to create and design and simulate complex models and scenes. And IFAS is a specific software for physics-based simulation, enabling users to simulate and visualize the behavior of objects and different materials and environments more realistically. So this image displayed on the slide was captured from the virtual environment that we created using IFAS. The goal of the study is to create simulated strawberry farm to test agricultural software and hardware applications. Our motivation is to develop a virtual environment that will allow us to generate large amount of data quickly and also simulate a wide range of scenarios and different conditions, which can improve the accuracy and reliability of the machine learning models. So the first objective was to develop ground vehicle for image collection in both simulation and the field condition. And the second objective is to generate synthetic images of strawberry plants. And the third objective is to predict strawberry yield using synthetic and real images. And this figure shows a simplified structure of our hardware and ROS and machine learning algorithm, both in the field and the simulation. We try to replicate exactly what we have and also do in the field in the virtual environment. The top image shows the ground vehicle equipped with a stereo vision camera and different lighting system. and also the LiDAR for capturing images of strawberry and also investigate the surroundings. And this system is controlled by RAS to acquire data and also for the navigation. And this Omniverse support integration with RAS, which means the virtual hardware system, in our case, simulated LiDAR, and simulated stereo vision, and simulated ground vehicle can be controlled using the same command in RAS, through RAS, and we can access those data in IFAS sim. And these are bigger images of what we do in the field. Typically, the simulated environment, the right side images is simulated environment for what we have in the field. We use the exact same physical dimension of plasticulture bed and plant spacing and soil condition, as well as vehicle and sensor specification, such as sensor mounting location, image resolution, focal length, and so on. And this slide shows the comparison of two generations of synthetic data that we created, generation 1 and generation 2. Synthetic data generation 1 shows a simplistic and cartoonish visual style. The plant and their texture appear less realistic and lack finer details. On the other hand, synthetic data generation 2 offers a significant improvement in realism. The plant exhibit more texture, providing a closer representation of real-world vegetation, such as leaf pattern, shading, and variation in plant structure, making it more visually convincing for the AI algorithm. And as I mentioned earlier, our objective is to create a virtual environment capable of generating vast amount of data rapidly and simulating diverse scenarios and conditions. In the top videos, we present the image data collected from the real field environment, that what we used to do before we used the digital twin and synthetic data. While the bottom videos shows the replication achieved within the virtual environment using IFAS sim. Interestingly, aside from the sensor distortion that we can see in the real image data, the virtual environment closely resembles the field environment in terms of visual representation. One thing that we learned from NVIDIA team, though, we can actually simulate even lens distortion as well. So we might try just to see if this will bring more accuracy for our AI algorithm. And one of the significant advantage of simulation is the ability to generate data across a range of illumination conditions, including transition from day to night, as well as simulate the wind and shadow effect. So you can see here, we can create different lighting, and also we can see that different shadow across throughout the day from the plant and plastic bed, and also from the equipment. And additionally, our ground vehicle is equipped with a LiDAR system, and the data shown here represent the actual field LiDAR data that we collected during field experiment. The varying colors here represent a different depth value of the object. We observe consistent pattern in this LiDAR data, such as greenish color representing the plastic bed, purple and bluish color for the plant canopy, and red color indicating the area between the rows. In addition, we have noticed a specific pattern, a green line here, along with the plastic bed. My student and I discussed about it, and we couldn't really find the reason why this is caused. So we were very intrigued, and we also do the same thing for the simulation. So we simulated this LiDAR data within IFAS sim, and we observed the same pattern as in this as in the real data. The plastic bed appeared around, as a greenish color, and the plant canopy shows purple and bluish colors, and the area between the rows also represented by the red. This is more zoomed view. And we also noticed this is a field LiDAR data that we collected, and this is a simulation data. As you can see, we have much more noise in the actual field data, we can see that it has a very similar pattern. But also, we noticed the presence of this green line along the plastic bed. So we wanted to do further investigation, what created this, and we discovered that this line was actually caused by the LiDAR hitting the wheel of the ground vehicle that we designed, leading to an undesired artifact in the sensing data. This finding actually made us to scrutinize our system design process by identifying the error in the virtual environment first, before we actually fabricate the machine or equipment that we want to deploy in the field. So in our study, we trained machine learning algorithm to detect strawberry fruit utilizing synthetic data with varying levels of detail to assess its impact on accuracy. This particular image served as a training data set in generation 1, describing a strawberry plant that appears nearly identical, lacking texture, and also featuring simplistic colors. We do not have any other immature fruit. Also flower looks exactly the same, but we wanted to test it nonetheless. But we expected poor accuracy for the result by using the simple images. However, to our surprise, the generation 1 data set demonstrated good enough performances. As shown in the images, even green fruit were successfully detected in the field images. This was trained using only 100% synthetic data with a very simple characteristic. So it was very interesting. Most of fruit were detected, but many of the missed fruit actually occurred for the fruit during the early stage of the fruit development, as shown by the arrow here, where the fruit still had a calyx attached. So we didn't have this data set for the generation 1. And this is the training images in the generation 2 data set. This data set has more texture, different maturity levels of the fruit. And also we do have a runner, but it is not shown here. At the bottom, it is the labeled images by colored masks that indicate the specific fruit object labeled by the IFAS sim. One thing I want to mention is that IFAS sim has a feature that enables automatic labeling and annotation of images generated within this environment. So this functionality is particularly useful when it comes to identifying and categorizing different objects such as fruit or leaf or runner. It enables the generation of large amount of labeled data very quickly and efficiently. And this is the result images using generation 2 data set. The colored area is detected fruit, and grayscale areas indicated the background. In this image, immature fruit with the calyx is also detected successfully as well. When we compared the result, this is very evident that synthetic data generation 2 outperforms synthetic data generation 1 in various aspects. Generation 2 achieved a higher number of true positive, and also it shows a higher precision recall and F1 score, indicating a better balance between precision and recall metrics. And also the accuracy of the generation 2 was significantly higher at 89%. Compared to 68% for the generation 1. This finding suggests that synthetic data generation 2 with a more realistic representation improved the performance compared to the generation 1. And the second table is from a different study that we conducted in the Penn State. I just brought this table just to compare for the AI algorithm that is trained using real data. So this table is from 100% synthetic data trained AI algorithm. So this result is actually coming from this study. We created machine vision system for apple yield estimation. We followed the same process that I described in earlier slide, but this is actually third prototype to increase the accuracy. So after our third trials, the performance of this real data for the apple prediction, yield prediction is about, F1 score is about 0.92. So actually the performance metrics achieved with the real data is higher. But when we compare this F1 score, and also this 0.92 is actually when we exclude the fruit from heavy occlusion, and when we include only fully visible to moderately occluded apple images. So when we compare this 0.92 with this 0.89, the difference is not that significant in my opinion. So this suggests that synthetic data has the potential to be a valuable resources, offering a viable alternative when real data is not available or limited. So we're currently working on expanding this system to include a robotic runner cutter. Our ongoing project aims to integrate the detection capabilities of what we have developed into a robotic runner cutter, allowing for automated identification of the runner and also removing the runners in strawberry field. Runner refers to a long, thin stem that grows horizontally along the ground. So this is a parent plant, and this is a daughter plant. Runners serve as a means of reproduction and expansion for strawberry plants, and these new plants are connected to the parent plant through the runner. So in agriculture practices, runners are often managed by cutting to promote better fruit production. But strawberry farmers, they already struggle for the labor supply, but the duration of this runner cutting season is overlapped with the harvesting season. So we do not want to compete workers for a runner cutter. They want to put more workers to the harvesting. So although this is a very important process, it's often neglected because of that. So we want to automate this process. So we created this runner detection and cutting mechanism for the digital twin in lab setting environment, because we don't have strawberry in the field yet, because the strawberry field season is not started. So this is what we have in the lab. We have a strawberry with a runner in the pot. So we create exactly same specification for the IFAS sim. And this is a runner identification algorithm. Although it did detect runner correctly, but still AI algorithm is confused with the actual stem with the runner stem. So we're working on it to improve the accuracy. And this video shows the integration of ROS comments for controlling a hardware robotic arm while simultaneously communicating with the IFAS sim. So this is what we have, and this is a IFAS sim. So when we make a comment to the ROS system, it can communicate with the actual hardware and the IFAS sim at the same time. And this is just simulation with the different types of robotic arm that we're trying to purchase in the near future. So our plan is to try reinforcement learning to train a runner cutter. So to detect the runner and then approach to the cutting location after the identification. Okay, so that was my presentation. For the summary, the turnaround time from concept to the product in agriculture technology is very costly and also time consuming. There are many reasons why we have so many challenges, mostly because of the limitation of the data in the field season. For the conclusion, leveraging synthetic data and the better simulation tool, more realistic simulation tool can help mitigate this risk. This synthetic data and simulation tool allows some more frequent and extensive testing and reducing reliance on limited real-world opportunities. And I'd like to acknowledge my PhD student, especially Omid. This is mostly Omid's work. I'd like to acknowledge their hard work for this study. And that was all for my presentation. Thank you. And if you have any question, please let me know.
Thank you very much, Dana. It's very impressive work. So we have about 5 minutes for Q&A. So if you have a question, please unmute yourself. You can speak up.
Hi, yes,
then,
I have a question.
Go ahead.
Sorry, so on the LiDAR screens that you were showing, are the colors just representing depth, distance, or texture, or are you running some kind of segmentation on those points?
Those are just depth information. We didn't do any segmentation for that because it shows different color because the plant has a different height and the plant bed is lower than that, so it has different colors.
I see, but could you do plant detection from those LiDAR scans?
I think so, yeah, because we're growing the strawberry on the plastic bed, so the difference in the bed between the bed and the canopy is consistent mostly. So I think so, yeah.
Okay, thank you.
Okay, we have so I think Rafa, you first raise your hand. Can you go ahead to ask your question, Rafa?
Yeah. Katie, you were first. You want to go first?
Oh, really?
Okay. All right.
Okay,
so
Katie.
Very quickly,
that's also okay.
Daeun, amazing. Okay, amazing.
Thank
really,
you.
really great work. Yesterday we were discussing the Omniverse that the university is trying. Are you working with them?
Yeah, actually we have a official collaboration project together. So we're working together for this project. Yeah.
Okay, so that's the high performance computing. Yes, because they mentioned a crop application, but they didn't give details, and I was wondering if this was the one. Okay, great. If there is any issues interfacing with them, remember I'm on the advisory committee. So, but it's great to see that this project is one of the ones being tested to see the opportunity that the Omniverse can bring to this kind of project. So fantastic work. Thank you.
Great, thank you.
Yeah, I agree. Great presentation. The synthetic data is a game changer, right? I mean, that can really change what we can do. So are you looking at any other synthetic crops to be grown? Are you working with just some strawberries right now, or?
Right now we're only working on strawberry, but we're the next step, we're trying to add disease component to it. So we want to use it for disease detection and the treatment for the disease in synthetic data. So, but so far we don't have any other crops for digital.
Okay, I suspect tomato is going to be knocking at your door really soon.
Yeah, yeah, I hope so, yeah.
All right, great job.
Thank you.
So David.
Can I ask a question while she's transitioning? Very quick one. So what about the differences between real data and the simulated environment, and can you add those to the performance indicators at the end?
Oh, can you say that again?
Can you add the loss of information between the real field to the simulated environment into the performance indicators that you get on the simulated environment?
I don't think I understood your question correctly.
So you have the simulated environment, you have the real world.
Yes.
You now use the simulated environment to do some of this virtual testing of your devices, detection, and things like that.
Yes.
But we understand that the simulated environment has some loss of information with respect to the real system. Is there a way to propagate those uncertainties in the first step, real, simulated, and add them into the findings on just the simulated environment?
Yes, so that's actually called sim to real gap. It's a whole different research area. So there are many techniques that we can actually reduce this gap. One is a randomization. We need to identify what is the key factor that cause error between the real system and the virtual environment. And then we need to randomize those parameters to create more challenges in virtual setting for the robotic system. So that's the one way. And the best way is to create the more realistic environment as much as possible, but that's not easy as usual. So yeah, so one of the reinforcement technique is those randomizing parameter for the environmental factors. Yeah.
Are you planning to add those to your testing? I mean, to your final
yes.
score? Yes.
Yes. Yeah. Absolutely. Yeah.
Thank you.
Yeah. Thank you.
Yeah. Thank you. Wonderful presentation. But I love there was, I think, a slide on the citrus block in Lake Wales.
Yeah.
Yes, like
That
so
was
I
actually
work
from my PhD dissertation.
Oh, I see. That's interesting. So I work primarily on citrus, and I'm also working on bamboo. So there was a question from Katie about other crops you would work on. So I know you are primarily focusing on strawberries, but is that niche to work on some perennial crops, especially like bamboo? Nowadays, trying to work on water and nutrient requirements for bamboo, but also there are so many configurations for citrus. Some are growing citrus in covers, and some are growing those on beds, and some are growing those in undercover systems. So I don't know if you have those kinds of innovations, especially management like canopy architecture, managing the pruning practices and all that. So I think those are innovations that I would love to see if you have those other big plans in your radar.
Yeah, the different types of crops definitely is doable. The way I did is actually I work with a commercial company for computer graphics to create this vegetation in graphics for the 3D models. But this IFAS theme, we can actually do the randomization process. So once you have the 3D modeling, you can randomize different maturity or different structure or different size. So you can make the unlimited amount of data, different data using this. So if you're interested, I can give you more information about it.
Thank you.
Yeah, you're
Okay.
welcome.
That's great. Those are very good questions. Thank you very much for a very good, robust discussion. I also have a question, but I think we're running out of time. So I will ask a question to Dana privately. So let's move on to our next speaker. Let me briefly introduce our next speaker, Dr. Chang Zhao. She's an assistant professor in the agronomy department. Chang received his PhD in geography from the University of Iowa in 2018. So Dr. Zhao's research is centered around the ecosystem services AI. She will be presenting on harnessing artificial intelligence for ecosystem service assessments across the scales to support sustainable land use planning and management. So Chang, would you like to share your screen? Yes, we can see your screen well.
Okay, so thanks for the introduction, Charlie. So hi everyone, I'm Chang. I'm a new assistant professor from agronomy. I'm also an affiliate faculty in the Department of Geography, University of Florida. So today my talk will be on quantifying ecosystem services with geospatial AI. In this talk, I'm gonna briefly describe the concept of ecosystem services, valuation approaches, and then why it's important that we take a spatial approach, and what are the geospatial artificial intelligence way that we can use to increase our capacity for the assessments. So the idea of ecosystem services has been existed for a long time, but it was popularized by the launch of the Millennium Ecosystem Assessments in 2005. It defines ecosystem services as the benefits people obtain from ecosystems. So the MEA assessed the consequences of environmental changes for human well-being, and it established the scientific basis for actions needed for conservation and environmental management. So the key findings of MEA involves that there was a substantial net gains in human well-being and economic development, but such gains have been achieved at growing cost of the forms of degradation of many services. So since the publication of MEA, there was a large amount of research trying to incorporate the concept of ecosystem services into policy and decision-making, and the field ecosystem services that integrates both environmental science and economics has been developed. So there are many classifications of ecosystem services. MEA classification is the most widely used one. And I also want to mention that there are like common international classification of ecosystem services used by the European agencies and also the US EPA National Ecosystem Service Classification. Here, I'm just briefly describe the MEA classification. So we have broadly 4 major categories of services. The first is provisioning, which includes food, fresh water, timber, wood and fiber, genetic resources, medications. And the second category is regulating ones. So ecosystem regulates climate, regulates air quality, water, disease, and also provide pest control benefits and pollination. And the third ones are those services that serve in the middle ground, which is the supporting services that it provides the foundation for many of the other services, such as provision of habitats, primary production, soil formation, and nutrient cycling. And the last one is the most intangible and hard to track services that involve cultural ecosystems. So this involves like educational, aesthetic value of the natural environment, cultural heritage, outdoor recreation, and a lot of the religious values and tourism. So it is well recognized that ecosystem services are important for human society. However, the values of services are not typically considered in policy and decision making. And so valuation is the process of quantifying the value of services benefits to people provided by a given landscape or habitat type in a defined location. So Costanza in 1997 conducted a global analysis of the entire biosphere, what's the total amount of services can provide it. So it estimated that on average, $33 trillion per year that cost like ecosystem services can provide. And it's actually in comparison to the global gross national product, at that time, it's like way larger than the global gross national product. And also the Costanza conducted the second analysis for the global loss of ecosystem services due to land use change. And it was estimated at about 4 to 20 trillion per year for this cost of services. So this is actually more than twice as much to human well-being as global GDP. So valuation of services cannot be conducted at a broader sense. Like what I mean is like valuation is always locally and contextually specific. So the first step for valuation is actually to identify the extent of ecosystem and the stock and the flow of services in a specific ecosystem in specific locations. So this actually means that there is spatial heterogeneity in the ecosystem's capacity to provide services, and also there's spatial heterogeneity in societal needs for such services. So there, in terms of this temporal scale, there are changes in ecosystem services over time because of the drivers such as land use and land cover change, climate change, and also a variety of land use management practices. So when we think about the supply and demand relationship of ecosystem services, benefits usually depends on where the service providing area are in the landscape in relationship to the locations of the beneficiaries. So there is an intrinsic spatial relationships between supply and demand that also influence the benefits to the flow of the benefits. So I would like to describe like a spatially explicit framework for ecosystem assessments, which relies on spatial data and approaches in order to systematically map the extent and condition of ecosystems and then to track changes in ecosystems over time. And also a lot of the assessments happened at the local scale, where we collected field data on certain types of services at the plot level. And however, we need to develop a strategy to upscale the observation to a broader landscape. And then also we to understand the flow of services from supply to demand to beneficiary locations. So this is a spatially explicit framework that I want to describe. And I think geospatial artificial intelligence is really extend our capacity to incorporate such framework in the assessments. So geospatial AI is an emerging scientific discipline that leverage the innovation of GI science, artificial intelligence, which involves machine learning, deep learning, data mining, and high performance computing to extract knowledge from big spatial data. This includes images collected from remote sensing. It also includes a lot of the spatial vector and raster data sets that's collected by a lot of sensors, including IoT sensors and also a variety of instruments. So by using geospatial AI approaches, we could conduct ecosystem service assessments in a spatially explicit way. For example, we could try to map land use and land cover and detect changes, and then link land use and land cover to the changes of ecosystem services. And also we could identify the vegetation dynamics and monitor vegetation changes over time. And if we collect local measurements of in situ measurements of ecosystem services, we could develop statistical models that try to predict indirectly or directly predict ecosystem services by linking socioeconomic and environmental factors and drivers to ecosystem service production. And also with the AI technologies, we could quantify uncertainties in such estimation and prediction. And also a key advantage of geospatial AI is that we could characterize both the supply and demand aspects of services because those heterogeneous spatial data capture both the social and physical dimensions of the globe. So I want to mention two dominant major types of geospatial data sets that we could leverage. First is the volunteer geographic information-based data for ecosystem assessments. VGI are important tools to gather spatial data on biodiversity and ecosystems. So because those, here is a graph showing the iNaturalist platform. So in iNaturalist, people post observations of plants, species, wildlife, and it published to, it's collected at the global scale and it's spatially explicit. It's a cost-effective way for us to monitor biodiversity at the larger spatial scale. And for some of the other types of VGI data sets, we could actually use those data to extract knowledge about human dynamics and so user preferences of ecosystem services, because this actually is more tied to the quantification of cultural ecosystem services and biodiversity, which is a type of supporting or a concept that's very closely related to ecosystem services, and researchers are trying to understand how biodiversity are related to services and vice versa. So VGI is a very important and very popular data sources that in the current field of GeoAI. It's one example is that it could give us ideas of how people use environment and whether they prefer certain type of services versus others. And this is related to recreation, outdoor recreation, and also aesthetic landscape appreciation. And another benefit is that it's provides a way to estimate those more intangible and non-material benefits compared to those traditional ways of data collection. So this is some very preliminary analysis that I conducted to basically try to extract what are the cultural ecosystem services usage on Flickr images. So Flickr is one of the most popular social media platforms for online photograph sharing, and there is a growing amount of research in cultural ecosystem assessments that utilize social media for semantic extraction of those recreation aesthetic type of services. And for here, like for these images, I applied the RES 50 CNN model pre-trained on ImageNet, which could provide us 1,000 categories of categories of common objects that we see. So this includes also objects like landscape features such as beach, mountains, rivers, and all those kind of natural elements. So you can see that it gives us the top 5 categories of features extracted in the image and also the probability. And then this is another examples of the ResNet 50. It gives us like accurate labels for these pictures. And outdoor recreation, like we could also potentially use CNN pre-trained models to look to extract semantic information about like human activities related to cultural ecosystem usage. For example, here is like they are bicycling and paddling, and this is canoeing. And also another examples of outdoor recreation extraction from social media images. So like this is a person on the motorboat, and however, there are also misclassification by the pre-trained model. Here it identified the killer whale is the top label. So this preliminary exploration give us an idea that pre-trained model is very helpful for us to extract patterns of cultural ecosystem service usage at larger scale. And there is a need for us to fine-tune the model to develop like supervised training models to better and more accurately predict those cultural ecosystem services, especially if we are trying to also like predict the other categories of cultural ecosystem services, such as spiritual, cultural heritage, educational, and those are more like hard to capture by just using the ImageNet about 1,000 categories. So another major dominant type of geospatial data we could leverage is remote sensing images for ecosystem services. So Earth observation are important tool because they provide very rapid assessments, and it becomes more easily available over multiple platforms. We have those Landsat series of images, but also from European space agencies, we have Sentinel-2, those the widely used moderate resolution satellite imageries, and those are very cost effective. It provides us regular, repeatable observations, and we can access those images to remote locations, so that could provide like a global view of the ecosystem, and to provide us a way to assess ecosystem services at a larger scale. So this is a plot that shows like how we can transform remote sensing data to ecosystem service value and flow. And so basically there are two areas that we could focus on. Is like one is the remote land cover and land use mapping, because land cover and land use is still the most widely used way of transforming remote sensing data to the quantification of ecosystem services. Land use and land cover give us idea of the extent of the ecosystem by type, and it also provides a proxy assessments of the ecosystem characteristics, such as their capacity to provide certain services. For example, forested and heavily vegetation-dominated land cover would have higher capacity to provide certain services such as water filtration. So the second group of, however, I also want to mention that there is such a limitation in land use and land cover mapping in the current practices because of the uncertainty and the accuracy of land cover. A slight change of the land cover, like misclassification, a slight change of the arrow could be propagated to the final ecosystem service assessment product. So it requires us to have a more transparent accuracy assessments and uncertainty assessments in land use and land cover mapping. AI-based approaches could help us alleviate such problem. And then the second ways of transforming remote sensing data is to extract vegetation indices and to quantify, to serve as a proxy for ecosystem conditions. This involves the use of a variety of vegetation indexes such as NDVI, EVI, and look at the phenology of the plants. And also we could get primary productivity product from existing remote sensing product and the leaf surface area as a proxy, etc. So there are a variety of indexes that represents vegetation, soil, and water characteristics that we can use. Those could be used as a variable for subsequent ecological models or production function models. And the last one I want to mention, like it's a separate set of like sensor. It's like an active sensor compared to those like satellite imagery, which is LiDAR and SAR. So those are like, we could provide us additional information about the 3D structure of vegetation. So we could, with LiDAR data, we could understand the height of the vegetation and the multi-layer vegetation structures and use those like complexity of vegetation as an indicator of, say, soil erosion control or like biomass. So we could use LiDAR derived metrics to quantify woody biomass and also subsequently assess the carbon storage in woody biomass. So I want to the next section of my talk will be focusing on some preliminary like analysis of one of my current projects that I'm doing over the summer since I started my position in UF in January. So this is a very preliminary analysis, but I want to share like what I'm doing, so you have an idea about the project, the progress of me. And so this is around land use and land cover mapping and change detection in arid lands of Kenya. So in Kenya, there is a very severe invasive species issue. The prickly pear cactus, which is also called opuntia, is one of the most widespread invasive species in these arid areas in Kenya, where extreme threats to biodiversity, ecosystem services, and human well-being. So studies have found that it reduced the foraging. It's a great concern for the rangeland and farmers in Kenya because it reduced livestock yields, it negatively impacts the wildlife habitat, deplete soil and water resources, and reduce the diversity of plants and animals. So, however, the extent of such invasion has not been fully understood, and there is a lack of spatial information on the status of the invasion in that area and the consequences on ecosystem services. So to properly manage this invasive species and to manage the ecosystems, to restore the ecosystems in the country, mapping and inventory of the species are necessary. So in this project, I use a typical like pipeline for land use and land cover mapping using machine learning based approaches. First, I prepare the data from satellite image data from Sentinel-2 to construct a time series from 2016 to 2023, 8 years of data. And so I use the supervised learning approaches to which involves like an annotation of the images to different categories of land use and land cover, and specifically focus on the characters identification, and then apply several machine learning approaches to train that several machine learning data algorithms to conduct the classification of land use and land cover. So for the data pre-processing steps, I acquire the images on Google Earth Engine, and also try to fix an optimum cloud cover, because cloud cover is a very big problem in that area, especially during the raining season from May to December. Basically, there's cloud cover is like over 20% for most of the months in the year. So we find that the images from March to May is actually the best. So, and then we also perform atmospheric corrections on data that's prior to 2019, because there's no existing like atmospheric corrected data in that period. So we conducted basically, we first look at, we explore the spectral bands and create a visual representation of the histogram showing case different classes and examine the spectral signatures of different land use and land classes. And we also utilize various bands and their combinations to try to visually distinguish specific land use and land cover classes as an exploratory steps in the analysis. And specifically, we want to design a stratified random sampling to create points for validation and sampling. So this involves creating a specific characters approximation band in our study so that we could find the potential regions for characters and speed up the process of training data annotation. So this is some preliminary, like this is the image showing the study area. And you can see there's characters in the rangeland and shrubland areas. And we look at the band 8, the near infrared band versus the RGB bands, and the near infrared band give us an idea of the potential region of characters. And we also specifically look at the spectral signature, the histogram of the characters category, and we found that this formula actually gives us an idea of approximates those distribution very well. So then we updated the existing land use and land cover map, which is provided globally by the Google Dynamic World. And however, there is missing that the thematic categories do not give us the characters distribution. So we updated the map with the potential region of characters. This serves
So Chang, we cannot hear you. Like Chang has some connection issue.
Yeah, we cannot hear.
So our image is freezing. Okay, clearly, I think our speaker has some internet issues. So I hope she can rejoin us.
Charlie, while we're waiting, who's our next speakers? Who's next month?
Sorry, I'm connected.
So, Katie, so we are still planning for next speakers. Yeah, well, yeah, we will announce later. So Chang, you had some internet issues. Do you want to...
I can wrap up in 1 minute.
Sure. Okay, so we are close to the end of 1 hour.
Yeah, I just have one, just like 1 to 2 slides to show. All right, I think I need to go to the current slide. So I want to talk about the timeline. This one, not from current slide. Okay, so we conducted some preliminary analysis, and this is actually the green spots show us the testing site design. And we are going to actually visit Canyon in the summer to collect ground observations of cactus and validate our machine learning model. And this is like the very early stage of the project. And by the end of the summer, we are trying to develop a UNet, which is a computer vision based model to identify cactus in the region. And the random forest will serve as a base model for comparison. So I want to just have one slide to talk about the GeoAI approaches for ecosystem service assessments. There are opportunities because we could leverage such massive amounts of data in different, in both social and environmental disciplines to quantify ecosystem services, and the artificial intelligence provides us flexibility in the algorithm and workflows to accommodate characteristics of those spatial processes, and to understand how, and also to help us scale up our modeling across different geographic areas. However, the challenges is that there are inherent data bias in a lot of the geospatial data, especially those from volunteer geographic information introduced by data user bias and sampling bias, and also training deep learning model, especially for those fine resolution land use and land cover, such as for those urban areas, are pretty challenging because the scarcity of high resolution labels for many ecosystem structures. And also, lastly, I also want to mention ideally, we want to directly predict ecosystem services at the larger scale by scaling up local observations. However, it requires us to have intensive ground sampling of services with strategic spatial sample design. But it's kind of, at this stage, there's not enough ground situation, ground in situ observation of services, those cross-site observations with common standards of measurements. So I think there is in the future, we need to move towards developing a good strategy for spatial sampling of ecosystem services across sites in different ecoregion and climate zones and geospatial locations, and also establish classification, have a common classification of ecosystem services. Yeah, that's all I have today.
Okay.
Thank you.
Thank you very much, Chang. So I know we are 3 minutes over 12 o'clock, so we will not have time for questions today. So if you have any questions, you can directly address to Chang through email. Katie just mentioned about our future plans for the seminar series. So I'm still working with the planning committee to invite potential speakers, especially external speakers. So we hope to make it a monthly or bi-monthly seminar series. I hope you all enjoy those seminars. So today I really learned a lot of things from these two speakers. I really enjoyed it. I also want to thank everybody for your support and the time. Do you have any suggestions?
Just one more question. Will the seminars be posted on a website, or how will they be shared?
You mean the recorded seminar?
Mm-hmm.
Currently, we have not developed the policy to publicize this recorded seminar. I think we will share per request based on individual cases. So if somebody really wants to see it, we will share the recorded link. Currently, we don't have a plan to post it on our website. But if there's a greater demand for that, I think we will consider that. Okay. All right. Thank you, everybody, for your time and support. I will see you, everybody, next time. Thank you, Dana and Chang.
Thank you.